final presentation in this session will be given by Iris Bennett from Grinnell College. She's been working with Scott Linder here at Ohio Wesleyan this summer. And the title of her presentation is Inference for the Correlation Coefficient in a Bivariate Normal Model Under Type 2 Censoring. Maybe working.
As Dr. H.K. said, I worked with Dr. Linder this summer, and we worked on doing inference for the correlation coefficient in a bivariate normal model under type 2 censoring. Here is an example of a bivariate normal distribution. It is characterized by 5 different parameters: the mean of x, the mean of y, the standard deviation of x, the standard deviation of y, and what we were most interested in is rho, the population correlation coefficient. What rho measures is the strength of the linear relationship between x and y. It can take any value from -1 to +1. When the absolute value is very close to 1, that means they're very strongly linear related. When you take samples from these distributions, you're likely to see scatter plots that look very linear. When rho is close to 0, that means that there's not a strong relationship between x and y. So when you take scatter plots, you're likely to see these sort of patternless looking ones. We don't actually know rho in experimental context, so we try to get at it by using R, which is the sample correlation coefficient. Here I generated 3 different samples with 3 very different sample correlation coefficients. One thing that's important to note is that when R and rho do not necessarily match up, these 3 could possibly come from the same distribution. So you can see when the absolute value of R is very close to 1, there's this very strong linear trend. When it's close to 0, you don't see much of a pattern whatsoever. Here we have a sampling distribution of R for when n, the sample size is 30, and rho is 0.5. We can use this to start making inferences. For example, if you were a researcher and you found an R value of -0.5, you could probably say, no, I don't believe that rho is actually 0.5 in this case. I mean, I generated several thousand different samples and didn't get anything near that. So that can't happen. We could also use this to estimate percentiles. We could go into the data and find where the 10th percentile lies, 15th, and so on. What we would really like to do, though, this took me a lot of work because I had to generate all these samples. I had to calculate their correlation coefficient. What we want is some kind of mathematically driven model that says, for any given n and any given rho, we know what this sampling distribution should look like. Unfortunately, with R, we can't actually do that. It's mathematically intractable. Luckily, in the 1920s, Sir Ronald Fisher came up with a solution for us. He found that if you use this transformation on R, the same transformation on rho, and then subtract and scale like this, you'll actually get standard normal distribution. That's very useful for us because we know about standard normal distribution. We know it has mean 0, we know it has standard deviation of 1, we know it's symmetric, and we can use this to make our inferences and then transform back and apply those inferences to R and rho. So our lives are good, assuming that we have full samples. But once we start censoring, what happens? So let's consider a hypothetical experiment that I'm going to be doing on monkeys. Sorry, people who love animals, but I'm going to wait for them to pass away, and I'm going to measure the amount of fat in their heart after death. Thing is, I have to wait for them to pass away before I can do it, so I can relate age and fat. And I just generated this data, so I don't actually have monkeys. I'm going to be waiting for 29 years for them all to pass away. And that's a long time. So instead, I'm going to actually have 40 monkeys, only wait for 20 of them, and wait 21 years instead. Well, the benefit here is obvious for me, in that I'm getting out of here 8 years sooner. The question is, can I actually get as good of inference from the sample on the right that I could have from the one on the left? Mathematically, our reasoning kind of falls apart here. We don't have these IID samples anymore, so we can't necessarily use Fisher's idea, but maybe it works. Unfortunately, it doesn't. Here I've generated a full sample, here a moderately censored sample, and here a severely censored sample. Now, if censoring had no effect whatsoever, all three of these should be identical. Pretty obviously, they aren't. You can see that the variation of this distribution is quite a bit bigger than this, just visually. But maybe that's not such a big deal because, I mean, even using the full sample case, we had to transform the transformation to get inference anyway. So let's do that. This looks promising. We have the same shape going on. It looks like they even have the same standard deviation. But our problem comes when we start looking at these sort of shift you can see. Here we're centered at 0, like we expect to be. But here we're already shifting. We're centered maybe more at -0.6 or -0.7. And by the time we get over here and we're severely centered, we're maybe centered at -1. And this is a huge problem for, we obviously can't apply the same distribution. So we'll have to find some kind of solution. So what we did was we tried to describe these shifts as functions of n and p, and then transform ZR stars that our new transform variable is standard normal. We then hope to use this new model to decrease our errors in percentiles and improve confidence interval coverage rates. So how we went about this was to generate these samples of ZR stars. For example, this one is where n is 30, p is 13, and rho is 0.9. And we would compare it versus the standard normal. So we would look at, say, the 5th percentile here compared to the 5th percentile here, and then record that shift. And we ended up with this huge catalog of shifts that we then tried to model using n and p. And we ended up coming up with this model, where positive e signifies a shift to the left from standard normal. So we have our model, but we wanted to test how well it was actually working. One way we went about this was using absolute errors of percentile estimates. In the center, we have the unmodified model. That's just using the standard normal without our added shift in. And you can see that there's actually some pretty high errors in here. We've got, say, 0.649 error, 0.580 error. Of course, with any error goals, we want to be at 0. And we get much, much closer when we add our shift. For example, we go from 0.58 to -0.067, or 0.440 to -0.003. That's not really across the board. To give you some idea of the patterns that we see in our errors, the black dots here are our errors, and the blue are using Fisher's unmodified. And we end up finding that we do worse, but not terribly worse when rho is 0.1. We do very, very well, and Fisher does not very well at all when rho is 0.5. And we both do poorly, but Fisher does far more poorly when rho is 0.9. Another test we used was looking at nominal 95% confidence interval coverage rates. So the idea behind a 95% confidence interval is using the value of R that I achieved from my sample, I want to make an interval. And then if I did this sample many, many, many more times under the same experimental conditions, 95% of these intervals should contain the true value of rho. And using Fisher's unmodified model, that just doesn't happen. You can see we have 85.3% confidence intervals here, 83.3% confidence intervals here. And if we're saying that we have 95% confidence interval, but we really only have an 83% confidence interval, we're really not as sure in our results as we really should be. So when we used our modified model, things looked a lot better. That 86.1% confidence interval changed to 95% confidence interval. That 85.3% confidence interval changed to 94.8% confidence interval. Again, it's not true across the board though. Again, those blue dots are Fisher's, black dots are ours, and now we're looking at 95% confidence interval coverage rates. Again, we see sort of the very similar trends. Fisher does better at us when rho is 0.1. We do much better than Fisher when rho is 0.5. And again, we do better than Fisher when rho is 0.9. some other things we kind of glanced at this summer, where we looked at 90% confidence interval coverage rates as well as 95%, found similar patterns, and we also made a model for symmetric censoring as well as rates. Thank you.
Okay, questions for Iris? Yeah.
For those graphs that are with row 0.1, 0.5, and 0.9, why is it the case? Is there significance that 0.5 is better? Like, does your model just do better? Or why does Fisher's do better with 0.1 and you don't? I don't know.
Trying to explain this without the picture. When we had to kind of average over all the values of rho since we couldn't actually put rho into our model. So because we used from 0.1 to 0.9 when we were generating these data, 0.5 was kind of in the middle. So that just happened to be kind of where our line landed, so it fits best at 0.5.
Why does Fisher's model then fit best at 0.1? Because
when they're censoring, when rho is close to 0, censoring doesn't really have as much of an effect because there's very little relationship between x and y anyway. Yeah.
So would it be feasible to have different models for different values of rho since they seem optimized for different values?
We actually looked into that at first, and we found that it worked really well if you knew rho,
Okay.
but we don't. But we're trying to get at it.
Okay.
Any other questions? Okay, thank you, Iris.